I'm very glad to have you here today. My name, in case you don't know me, is Tom Carpenter, and I'm the CTO here at CWNP. We are a certification company helping people to master 802.11n wireless, as well as 802.11ac and 802.11b and G and all the rest. So we're all about the standards-based wireless. And what we're doing is, for this last part of the year here, we're starting a series of webinars on 802.11ac. And this first one is on the new features in this new implementation or amendment to the standard. Then we'll begin to do other future specialization webinars. So, for example, the next webinar will probably be on 802.11ac planning, to make sure that you know how to plan for it and implement it when you're ready to go in that direction. And then we'll also be looking at some very specific subcomponents of 802.11ac as we go along, such as MultiUser MIMO and other technologies of this sort. So today it's about getting an understanding of the new features. I would put this at a 100 level course if we wanted to talk about it in that terminology. It's not going to be advanced, so everyone should be able to grasp everything. But even those of you that have been studying 802.11ac for a while may run into some new thoughts or ideas. So at the very least, keep me in the background and listen while you're doing your other work. So let's jump right in here and start off with a brief overview of our certifications. I'm sure most of you attending this presentation are aware of our certifications, so I'm not going to go into great depth on them, but I just want to remind you about these different certifications, what they are, why they matter, and who is targeted by the different types that we have. The very bottom of the slide here shows the CWTS certification, which is the Certified Wireless Technology Specialist. And this is an individual who is really just starting out in the wireless industry. We sometimes say non-techies, but believe me, there's some technical information in CWTS. So you do need to be able to wrap your mind around technical information to understand the concepts, but it's not really for those that have been entrenched in wireless for a while. It's for those that are just starting out, for project managers that need to understand what their techies mean when they're talking to them during a wireless project, for sales professionals who are selling wireless products, these types of things. It's also a great stepping stone to CWNA, so if you're brand new, it's often good to start with CWTS and then take the CWNA exam, even though CWTS is not required. So it's not a prerequisite to CWNA. It's just a recommendation. So if you're starting brand new, you haven't really worked in wireless, I would say start with CWTS and then go to CWNA. But if you've worked with wireless for a while, you can probably jump right in to the Certified Wireless Network Administrator, or the CWNA. And this is really for that person that is the individual who's managing the wireless network, who's working with the wireless technologies and so on. So this is what you might call our flagship certification. It is the foundation of moving on in our certification path. So in other words, you can't become a CWSP, as an example, without having your CWNA certification. Now, you can take the CWSP exam first, but you're not a CWSP until you've also passed the CWNA, and therefore it's most logical to do the CWNA and then the professional level certifications. So you do your CWNA, which is your well-rounded understanding of wireless technologies at a moderate level of knowledge. You could definitely build a wireless network and implement it with CWNA. But then you can specialize to go to the professional level in 3 different categories: design, security, and troubleshooting. And so CWDP is about design, SP is about security, and AP is about troubleshooting. And of course, then the pinnacle of success in our certification tracks is the CWNE, the Certified Wireless Networking Expert, or Network Expert. And at this level, you haven't taken an additional exam. You have instead applied your knowledge in the real world. You've worked in the industry for at least 3 years, and you have passed all 3 professional level exams and acquired all 3 certifications, and then you submit an application to become a CWNE. Today, that is sent before a board of advisors. The board of advisors looks at your application and then determines from that whether or not you should be approved as a CWNE. It's a very big honor to be a CWNE because it's not like a lot of certifications out there. You're not just taking a test and bang, you're a CWNE. Instead, there is a board of advisors, 6 of us in total. I'm one of them representing CWNP on the board, and then there are 6 others who actually are independent from CWNP but are themselves CWNEs. So they look over those applications and then approve or reject them accordingly. So it's definitely something well worth pursuing in your career. These are our certifications. Of course, you can always learn more at CWNP.com. In the upper left corner, you can learn all about our certifications there. Now, the agenda for today, then, as we talk about 802.11ac, is going to be to look over what has now become known as Wave 1 and Wave 2 with 802.11ac. So we'll kind of take it in that approach, biting off the chunks in that way. And then we'll talk about what I call the maybe later features, and we'll talk a little bit about what different hardware vendors are actually making some 802.11ac stuff available today. So we will begin with Wave 1 understanding, what is out there right now and will continue to be there for the next few months, and then what will be coming sometime later next year or even into 2015. So we'll kind of take that approach as we go through this. And to give you a time frame, we'll probably take about 35 to 40 minutes to cover all of the content that we have today prepared. But I would encourage you in that side chat bar, where I appreciate all of you letting me know that you've been able to hear me. You can just type in a question. I'll glance over there and monitor that when I see new things pop up. And if you ask a question, I will do my best to answer that as best I can with what is before me today. So I'll be glad to answer any questions you might have as we go along about these topics. Do keep in mind, again, we'll be doing more advanced and in-depth webinars for free, just like this one later on, to help you continue your learning of 802.11ac. This is the next big thing, and we want to help people learn about wireless technologies as they come along. My name, Tim, is Tom Carpenter, and I'm the CTO here at CWNP, which basically means that I design the objectives and set the direction for the certifications with the assistance of a large pool of CWNEs that help me out. Okay, so let's jump right in here and continue. First thing you need to know, real big, loud and clear, 5 gigahertz only. Okay, so 802.11ac is not really in 2.4 gigahertz. You'll often see individuals say, here's an 802.11ac device, it works in 2.4 and 5 gigahertz. And you see this in a lot of consumer packaging that's out there right now at your electronics stores. Well, the thing to keep in mind is that what you have in the 2.4 gigahertz band with 802.11ac devices is actually 802.11n. So that device is implementing the HT physical layer in the 2.4 gigahertz band, and it's implementing the VHT physical layer in the 5 gigahertz band. So VHT stands for very high throughput. They got really creative. It was high throughput with 802.11n, so 802.11ac was very high throughput. I guess the next one is going to be something like either VVHT for very, very high throughput or EHT for extremely high throughput. I'm not sure where they'll go, but that's where we are right now. So VHT is the name of the new physical layer that gives us the promises of 802.11ac in the 5 gigahertz frequency band. And then HT is the old 802.11n physical layer that is still operational in 2.4 gigahertz. So if you get a dual band 802.11ac consumer router, even if it runs both bands at the same time, you're running 11n and 2.4 gigahertz effectively. It's not really 11n, okay? It's the HT physical layer, but it's what colloquially we call 11n. And then in the 5 gigahertz, you're running VHT. And so it is 5 gigahertz only. So all the enhancements that we're going to talk about today, all the new features we're going to talk about today are operational in 5 gigahertz frequency bands. So that means obviously you're dealing with clients and APs that are going to have 5 gigahertz radios in them for this support. So with that said, let's talk about Wave 1 and what we're really looking at here. The first thing is 3x3. The initial devices coming out are 3x3. And what does that mean? Well, it means that they have the ability to use 3 spatial streams. They're actually 3x3x3. So there are 3 receive antennas, there are 3 transmit antennas, and they can all 3 transmit and receive at the same time. Hence 3x3x3 or 3 spatial streams. Now, that was there in the latest 802.11n devices. So the existing 802.11n architecture from a physical implementation of the number of radios is still there, but it's enhanced with wider channels and new modulation. So we've got 3 streams, a maximum of an 80 megahertz channel in the devices that are coming out, 400 nanosecond or 800 nanosecond, but the short guard interval is 400 nanoseconds. And so this means that the delay between the communications of frames is half the weight. That's the guard interval. 256 QAM or QAM modulation, depending on who you ask how to pronounce that acronym, and a 5/6 coding rate, which is the highest bits to codes rate that you can get. There is 3/4 coding rate as well, but this is what you have to get this promise you see on boxes of 1300 megabits per second or 1.3 gigabits per second. You have to have 3 streams, 80 megahertz channel, 400 nanosecond short guard interval, 256 QAM, 5/6 coding rate. This is what you're looking at. And to answer the question of whether these slides, by the way, will be available, the answer is yes. I will post a blog post at CWNP.com and link to the slide deck for download. So that way you'll be able to get the slides from that post. So if you check within the next day or two, you should see the new blog post at CWNP.com, and you will see that it links to the slides. So this is important to know, and the reason this is important to know will be revealed as we continue talking about 256 QAM modulation later on. Okay, 256 QAM modulation is a very sensitive modulation. And what I mean by that is you have to really get a good quality signal in order to use 256 QAM. And you'll see that when we talk about some of the requirements of actually implementing that modulation. So what I want you to know is just that the devices that are there now are 3x3. We're going to see 4x4 devices coming out next, obviously, and then we'll see what happens after that. But wave 1, 3x3, and this is partly a factor of we've already known how to implement this as a hardware concept, in that we've implemented radios and radio chains with 3 antennas and so on. So we already know how to do that. We also already know about power provisioning in this kind of a scenario, and so we're better prepared for 3x3 first wave 802.11 AC devices than we would be for, say, 4x4. And this is particularly true of our infrastructure. 3x3 is throttling us back. You're seeing right here the maximum data rate of 1,300 megabits per second. Well, at 1,300 megabits per second, that's the Wi-Fi side data rate. Now, most of you probably know that we're talking about a big difference between data rate and throughput or useful data, what we might think of as user data, the stuff that's going through the network, right? Not overhead. Well, when you get rid of all the Wi-Fi overhead, you're going to be under 1 gigabit per second. So we still are able to function quite well with a gigabit Ethernet link on the back of our AP connected up to our switch and manage any data that's coming through that AP. And that's here in wave 1 where we've got single user MIMO. And so right now, we don't have to worry about increasing our back-end links from our APs to the switches or anything like that, and we can begin implementing 802.11 AC with this technology. So this is what we would call wave 1 from a perspective of the number of radio chains. And note, when we say 3x3, by 3, that means you have to have 3 radios connected to 3 antennas in order for this communication to happen. Now here we have the second part of wave 1, and that's an 80 megahertz channel. We know that 20 and 40 megahertz channels were available in 802.11n. We typically implemented 20 megahertz channels in 2.4 gigahertz and 40 megahertz channels in 5 gigahertz. Well, 80 megahertz channels are commonly available in your current 802.11 AC devices that are out there. This effectively doubles the bandwidth, which of course gives you increased data rates, but it must be carefully planned. Even though we're dealing with 5 gigahertz where we have a lot more channels, it's a lot different planning for 80 megahertz channels than it is for 40 megahertz channels. We don't have the time today to get into massive detail about all of the different things that we have to deal with here, like DFS and TPC and these other technologies that impact what channels we can use and in what frequency space in that unlicensed 5 gigahertz band. But we do need to carefully plan. And that's something that in the next webinar, as I said, we'll talk about 802.11ac planning. We'll get into a lot more detail about those careful steps we have to take in planning our channels and so forth for 802.11ac. But it is an 80 megahertz channel, and that's a significant impact. And remember, on the previous slide, it was the requirement that if we're going to get to that 1,300 megabits per second, we're going to need an 80 megahertz channel to do it. So you can't deploy with 40 megahertz channels and get 1,300 megabits per second. You have to deploy an 80 megahertz channel in order to accomplish that. And that's what we see here. This is just a spectral mask borrowed from the IEEE 802.11ac draft standard. And it looks, if you've looked at those before, it looks just like the old spectral masks for all the other OFDM implementations that we've had. And we are still implementing OFDN, orthogonal frequency division multiplexing. That's still the kind of modulation that we're implementing here for 802.11ac. We're just increasing the frequency space and therefore the subcarriers and all the rest that we can implement in order to get more throughput. Now it's time for us to talk about one of the big pieces of noise that is out there related to 802.11ac, which is very important to understand and to comprehend where it's useful. So you'll hear about 256 QAM. And some people say QAM, some people say QAM. It stands for Quadrature Amplitude Modulation. It doesn't really matter to me how you pronounce things. I'm not big on worrying about how people say things. I don't care if you say MIMO or MIMO. Probably MIMO is more accurate to the words that the acronym stands for, but that's up to you. Different parts of the country might even say it differently. But here in Ohio, I usually say QAM, I usually say MIMO or MIMO, depends on how I feel that day. So I don't really care how you say acronyms. That really doesn't matter. What matters is that you know what they mean and what they're representing. And when we talk about QAM, we're talking about a modulation type, and we have different levels of QAM that are implemented already in 802.11n up to 64 QAM, and that's what we see here on the left. And so this is what's called a constellation, and it just helps us represent where the phase shifts and the amplitude shifts and so forth are that end up implementing this modulation scheme. And so when you look at this, the big thing to note, and the slide here doesn't represent it perfectly because I've got my 256 QAM image much larger than my 64 QAM image. It's probably better to have them both the exact same size, because then you can really see how much more separation there is between the 64 QAM constellation points and the 256 QAM constellation points. Now, don't worry too much about, what is constellation and all of that. The big thing to get out of this image right now is that there are a whole lot more byte values that we can represent with 256 QAM than there are with 64 QAM. And notice the 256 QAM constellation, which by the way comes right out of the 802.11ac draft, it actually shows you the bits that these different constellation points represent, or the bytes we should say. So they're kind of hard to read on the slide because I've had to shrink it down a bit, but you can see that they represent things like 0101, 1001. And so we can see the bytes that are being represented here. And by the way, when you hear the term byte, we always think 8 bits, don't we? But a byte doesn't have to be 8 bits. You can have a 9-bit byte, a 6-bit byte. You can have different bit levels in bytes. That's why a lot of standard documents use the term octet instead of byte in order to refer to an 8-bit byte, to be very specific. But the point is that each one of these is representing a byte, and they're also representing bytes in the other QAM levels. It's just that they're smaller bit size bytes. You might say it's a smaller chunk. And so if you do the math, if you think about it, you go from 64 QAM to 256 QAM, you have 4 times as many things that can be represented by one communication, right? So therefore, it's logical that we are going to increase the data rate and the throughput by going to 256 QAM. Now, it's important then to think about, all right, so what range can I use this? Because I'm sure you've noticed that with 802.11n already, as you get farther away from the access point, you are reducing your data rate, right? You've got this data rate shifting that happens as you move farther away from the access point. Why is that? Well, it's because the access point doesn't like you as much because you're getting farther away from it and it doesn't feel that good relationship connection that it used to feel. Okay, I'm kidding, but actually that analogy is sort of serious because the reality is it doesn't feel the same relationship. It's getting mixed signals from you, you might say, and so we have to shift back to a slower communication technology, hence lower data rates, that has more accuracy in communications with weaker signals. That's really what it comes down to. And you can see, and that's why I have these two QAMs side by side here. So you can see that there would be a lot more space in even a 64 QAM modulation for 802.11n than there is in a 256 QAM modulation for 802.11ac. And so because of this, you need a stronger signal to get 256 QAM. Some of those who've done testing, like Matthew Gast with AeroHive, he reports in his 802.11ac, a survival guidebook, that you need about 5 dB better quality signal to get 256 QAM instead of 64 QAM. There is some hints to what you could likely expect in the 802.11ac standard itself. In the standard, it talks about what you need to have as far as some signal in dBm in order to actually achieve 256 QAM. And they're saying neg 48 with 160 megahertz channel, neg 51 for an 80 megahertz, neg 54 for 40, and neg 57 for 20. And that's with a 5.6 coding rate. With a 3.4 coding rate, there's about 2 dB less sensitivity. So what that means is you could do a neg 50 for 160 megahertz channel, a neg 59, for example, for a 20 megahertz channel. It is important to note that the channel width, wider channels do require a better signal quality to achieve 256 QAM. So in other words, if you're using a 40 megahertz channel, you'll probably be able to be a little farther away from the AP, and I'm using very colloquial speech there because it's not all about distance from the AP. There are many other factors that apply. There are interference sources and different reflection patterns and things like that. But generally speaking, a little farther away, and you might be able to get a better distance then and still have 256 QAM with a narrower channel. But now you've got a narrower channel, right? So therefore, you're still not going to have as good of a data rate as you would with a wider channel. So obviously there are these things that balance out. Now, one thing to keep in mind is there's pretty strong attenuation that occurs with walls, right? And so one thing to keep in mind is that the likelihood of putting an AP in one room and then going to another room and being able to establish and maintain a 256 QAM connection is much less likely. And so if you need 256 QAM, you might end up in a situation where you need an AP in every room, depending on, and I want to be clear, depending on the size of the room and the wall materials and other factors that could impact that. Now, do you have a chart of RSSI values to channel widths? Well, you know, that's been a tough one to come up with so far, Corey, because a lot of the vendors are slow to release that information, and they're still really just starting some of their 802.11ac rollouts, and I'm talking about enterprise vendors. We almost never see this valuable type of information from consumer-grade vendors because they really don't care. Their pitch is, put our router in your house, and it covers your whole house, and you're just done, and even though you might have an 802.11b level signal when you get to the other end of your house, hey, you're covered, right? So, so therefore, we don't see that from the consumer rollouts, and those are the largest rollouts right now of 802.11ac draft standard devices. So we'll have to wait and see on some of that, but that is something that I'll be providing more information. I'm digging through all the literature from the vendors that have anything at all. So when we do our webinar, probably in November on 802.11ac planning, I should have a lot more valuable information for you in that realm, Corey. And what I'm going to do is aggregate some of this data that I can get together from vendors. I've already got some of it, but I'll be bringing it together to help you out with that. The question is, would I recommend open space for applications requiring 256 QAM throughput? Or open space are very close. Okay, so what I mean by that is, you know, if you're in a house, then you might put an AP on a wall in the house, and on the other side of that wall still get 256 QAM, or for that matter, even in a conference location, right? So you might be able to put an AP on a wall in one conference room, and then in the room on the other side of that wall, you may still be able to get 256 QAM. It's just going to depend on wall materials and a lot of other factors, and that's why, you know, site surveys are still going to be important for 802.11ac like they have been for earlier versions of 802.11. It's just we're looking for different things now, and now the thing to keep in mind, okay, 256 QAM, we're talking about really high data rates and throughput rates. And it is an important thing to ask, do we really need that? And is that the main thing we're going after? Or are we going after the fact that we can get 64 QAM at greater distances with 11AC than we did with 11N? So it improves, in other words, our range with 802.11ac. It improves our range with in several different ways. And therefore, even if we're at 64 QAM, the old 802.11n modulations, we can still get a little better performance. And also keep in mind that 256 QAM is not 256 QAM. There's two kinds, and I've kind of hinted at it. There's 5.6 coding rate and 3.4 coding rate. And I don't have the time today to get into depth on coding rates, but basically it's the number of actual data bits versus redundant bits that are being sent in order to get your information through and be able to ensure that it's accurate. So what I would suggest there is, you can take a look at the draft standard if you can have a copy of that. You can take a look at Matthew Gast's 802.11ac survival guidebook, really thin book, and you can get a little more information on that. But that's something to keep in mind too. So you could shift from one 256 QAM with 5.6 encoding back to another 256 QAM with 3.4 encoding, potentially before you would have to shift to 64 QAM. So there is the possibility of having a little extra range and yet not quite the highest possible data rate or throughput there. So that's 256 QAM, and we've spent quite a bit of time talking about it, but that's because it is one of the more important enhancements, and some understanding there is important. And ultimately, there will be testing that's done. Different vendors have different antenna technologies, and so with those different antenna technologies, even if they're proprietary, like Ruckus has some proprietary antenna technologies, when we see those technologies used with 256 QAM, we might be able to see even greater range and going through a couple of walls, potentially, again, depending on materials and distance and a lot of other factors, just how far 256 QAM can go. Definitely, though, an 802.11ac device sitting in your living room and streaming HD video to it from the couch, hey, that's going to be wonderful. Okay, so Wave 2, let's talk about that now for a little while. With Wave 2, what we're looking at is the hardware that comes either late next year or into 2015. 4x4x4 is sure to come, so we're going to go up to 4 spatial streams and maybe even beyond that in very short order after it. But this is going to give us higher data rates again. So when we go to 4x4x4, it's going to up the data rates higher than the 1300 megabits per second that we have now. And those tables are all in, again, the 802.11ac standard. Once it's ratified, you'll be able to buy it easily and get it for a short period of time, and eventually it'll be free. But again, all those stats, they're around the internet in different places. They're in Matthew Gast's book on 802.11ac, which I highly recommend. So you can get those tables to get all the exact numbers. Just to say 4x4x4 equals X is not an accurate statement, so I'm not really throwing out numbers related to this now, because there are all kinds of things that impact it. Yeah, you're 4x4x4, but what modulation are you using? What coding rate are you using? Obviously, all of that impacts it. If you're familiar with MCS from 802.11n, the modulation and coding schemes, we have the same basic concept in 11AC, so we've still got these tables that break it down in the standard that tell us if you have this many spatial streams and you have this modulation and you have this guard interval, etc., then here's the data rate that you get. Now, one other thing is we will see transmit beamforming more frequently as well. Some of the chipsets already have the concept there, but this is something we never implemented in 11N, even though it was in there. And the reason was because it wasn't standardized. So there were different beamforming methods, and the concept was, for one vendor, why should we do all this effort to implement it when it's not going to work with the AP that the customer has, and etc. So it really wasn't implemented. Now we have explicit beamforming as the only kind that is required or defined in the standard. So explicit beamforming means we're going to communicate back and forth from the client and the access point. So they're going to talk to each other and say, hey, here's what I'm seeing in the channel. And this information is used then to do the beamforming, rather than the alternate, which is implicit beamforming, where the AP just tries to guess channel conditions and then does the communication. Explicit beamforming was chosen because it is better for implementing multi-user MIMO. So when you implement that, you want to have this ability to really know your communication link well, and therefore be able to form the beam in the direction of that individual device with multi-user MIMO. Now, let me just briefly deal with this beamforming and give you a very high-level understanding of what it means. So you've got multiple antennas, right? The concept of beamforming is to use intentional phase shifting or alterations and send out the waves in different phases, if you will, or the waveforms, so that they are reflecting through the environment or moving through that environment in whatever way they do and arriving at the receiver with phase accuracy so that you get an increased signal, and therefore you can have a greater modulation rate at a greater distance, and then that gives you therefore better performance over greater distance. And this is the concept in general of beamforming. Thanks, Sean, for that link to MCS data rates, just to draw everyone's attention to it. In the chat, there is a link there that Sean has provided to you for those data rates. So explicit beamforming helps with that, to understand the channel and then do the proper phase modifications and create that better communication link over distance. Now, another thing that Wave 2 is going to bring is 160 megahertz channels. Now, here we have to think a little bit about some proper planning. Okay, so 160 megahertz channels in 4x4x4 configuration could accomplish data rates of up to 3,466.7 megabits per second with a short guard interval, or with the traditional or long guard, whatever you want to call it, the 800 nanosecond guard interval, 3,120 megabits per second, roughly 3 gigabits. Okay, so somewhere between 3 and 3.5 gigabits per second is what we'd be looking at with 4x4x4, 160 megahertz channels. And that's a really good communication rate. Now, this does obviously make you step back and say, okay, now a gigabit Ethernet port in the back of the AP is not going to be enough. Maybe we could do multiple gigabit Ethernet ports. Maybe we could do one 10G port. But the point is, 1G Ethernet port is not going to be good enough on the back of that AP to handle the data rates here. Well, more specifically, the throughput. The data rate's not the concern, it's the throughput, which is certainly now potentially going to be more than 1 gigabit. Now, it is important to know that 7 gigabits per second, and you'll hear that, 802.11ac gives us 7 gigabits per second. Well, it actually gives us 6,933.3 megabits per second. But to do that, you've got to have 8 by 8 by 8. And we're not going to see anything like that in the very near future at all. Okay, and I'll talk a little bit more about that later on. So for now, let's just say we're not going to see that in the very near future. So that is something coming to us down the road, sometime off into the future. But the bigger thing about 160 megahertz channels, and this is something we'll talk in more depth about when we do our 802.11ac planning webinar later this year, that is that when you're dealing with 160 megahertz channels, you begin to run into similar problems that we've already experienced in the 2.4 gigahertz band. So in the 2.4 gigahertz band, we had, you might as well say 3 non-overlapping channels, right? Worldwide, some people argued for 4 and things like that. But generally speaking, we look at the 4 non-overlapping channels, or I'm sorry, the 3 non-overlapping channels. So the issue was then we implemented 802.11n there. We said, don't use 40 megahertz channels. Of course, people did it in their houses all the time and things like that because we don't care about our neighbors, right? But at work, when we're implementing multiple access points in the enterprise or the business, we don't want our access points interfering with each other. So what we did is we implemented 20 megahertz channels in 2.4 gigahertz. There's a similar phenomenon with 160 megahertz channels in 802.11ac. And it's something that we'll definitely want to be thinking very carefully about as we plan. And I think we're probably going to see many people going with just 40 megahertz channels because they say that's all we need. The throughput we can get out of that is good enough for an individual client connection. Others will go with 80 megahertz channels, and it'll probably be pretty rare to do 160 megahertz channels, except here at my home office and in my house. And you might do it too if you don't care about your neighbors. Okay, wave 2 is multi-user MIMO. This is another thing that we'll see. So transmit beamforming for multiple users is an oversimplification of how to use this, but it's reuse of the channel space. The client needs to support transmit beamforming because it doesn't really know multi-user MIMOs going on per se. There's some communications there, but it's really about the AP being able to support this and to simultaneously transmit to multiple users. And this is where we're going to get what you may think of as switch-like behavior. Okay, one of our CWNEs and one of the elite wireless people in the world today, Keith Parsons, often says to people, an access point is a hub. And very true. This is the way we've always traditionally thought of an access point. An access point is a hub. And so you want to think of it like that. And when you think of it in that terminology, you realize that this is true because all communications really go to all devices that are part of the wireless LAN, that are part of that basic service set, whether they're for them or not. So they can see them, they just ignore them effectively if they're not for them, right? Well, with multi-user MIMO, the access point does sort of kind of start to get acting like a switch. And so what it's going to be doing then is with transmit beamforming and with subcarriers and spatial streams have the ability to communicate to multiple devices simultaneously on the channel space. So this is something that we're going to get to see with standardization. Now, some vendors have done some similar conceptual things to this through proprietary methods, but this is going to be standards-based, using standards-based transmit beamforming, using standard methods to implement it, and that means that you're going to be able to eventually just buy any vendor's hardware, any vendor client chipset, and you'll be able to take advantage of multi-user MIMO. Now, obviously with multi-user MIMO, again, let's say we've got 4x4x4, right? With multi-user MIMO, you're not going to be doing 4x4x4 to each user, are you? Because you're going to be using maybe 2 of the antennas for one user and 2 for the other. All right, so the thing to keep in mind is that with multi-user MIMO, even though we can send to multiple users at the same time, we couldn't possibly send to multiple users at the same time at the absolute maximum data rate that that AP could potentially support if it wasn't doing multi-user MIMO. And so we're sacrificing individual link throughput or data rate in order to get greater overall throughput or data rate, because now we're communicating with multiple users as separate streams at the same time, if you will. Now the benefit then is better overall throughput, and that's usually more important to us, isn't it? So we get better overall throughput because the reality is still each of these users, we're talking about even on a very bad link, maybe 50 or 60 megabits per second, very, very bad link there. So obviously we're dealing with some really good throughput compared to what people are used to getting in the past. Okay, let's talk about the maybe later. Now, the reason I've said maybe later for 8x8 is we've got to answer this question. Are we really going to see the 8x8, that 7 gig promise? Well, yeah, we will. We are going to see 8x8. It will not happen with 802.11ac. It might happen with 802.11xyz. Now, I'm saying that facetiously, but the point is that yes, there will be some standard eventually where we're doing 8x8 and probably beyond. But we probably won't see it with 802.11ac. This is Tom Carpenter's opinion, okay? So if you disagree with me, that's fine to disagree with me. But I see it being kind of like 802.11n. We never saw the 4x4 until 802.11ac is coming along. We saw 3x3. I think we'll see similar things with 802.11ac. We'll probably likely see other technologies and other advancements coming along in new physical layers before we get to 8x8. But you know what? If in a few years we have 8x8x8, 11ac, nothing else has come along for the physical layer, you can all send me an email and say, haha, Tom, you were wrong. It didn't work that way this time. Because as they always say with the stock market, right? Past performance is not a predictor of future results. 802.11n, however, never saw it. I emphasize here yet because maybe we'll see some 4x4 in the 2.4 gigahertz with some of the new dual band 802.11ac devices that come out. We'll have to wait and see. So maybe later. Now, getting hardware. At the consumer level, and I'm not by any means saying these are all of the vendors' devices that are out there at the consumer level, but these are ones that I have right here in my lab that I can set up and use Spectrum Analyzer and take a look at the quality of the signal and these kinds of things. So I've looked at some ASUS Buffalo D-Link Linksys from the AP/wireless router side, and on the client adapter side, Netgear and Buffalo. There are others too that are out there. These are just ones that I've worked with. So the important thing to keep in mind is, a lot of people ask, can you do spectrum analysis for 802.11ac? Well, the answer is absolutely, because spectrum analysis is about the RF energy, right? It has nothing to do with modulation. So you don't have to be able to demodulate. You don't have to be able to decode frames. You don't have to be able to do any of that stuff that you do with protocol analysis, right? So that just doesn't matter. So with spectrum analysis, sure, just take your spectrum analyzer you've been using forever and fire up an 802.11ac AP, fire up an 802.11ac client, take a look at the results. I've done that with several of the consumer grade devices so far, looking at what we're getting as far as quality of signal. What I mean by quality of signal is when you look at spectral masks, for really good quality hardware, they look, let's just say, more like that spectral mask we saw earlier for an 80 megahertz and a 160 megahertz channel. And when you look at lesser quality hardware, you tend to see spectral masks that, well, they just are unstable. They shift a lot and they don't always look as good as some of the better grade equipment. But the point is that you can get this consumer grade equipment, play around with it. Man, there's some phenomenal throughput rates that these 802.11ac devices are getting, even in consumer grade equipment. So it's definitely something well worth looking at as well. When it comes to enterprise hardware, the issue here is right now we have Cisco, Aruba, and Meraki saying, here are devices, they're for sale, you can get them. And other vendors are coming along very quickly, getting theirs up to speed as well. So, yes, you're right, Cisco and Meraki are the same, but I'm talking about the Cisco 802.11ac add-on module for Cisco devices and the Meraki device that's being sold separately. So there are separate devices from the two of these that are being sold under the brand names. But you're right, they are the same company. That's right, everything's going to be Cisco in the end, right? Let me answer another question here. How are you seeing vendor interoperability in days past with emerging standards? Interoperability was bad. You know, I have used the 802.11ac adapters that I have from Netgear in Buffalo, and I've used them against all of my 802.11ac routers, and every one of them works fine. So they all work the same. I really didn't get any significant difference in throughput among them at all. So I can't really say that there were any problems there. Now with the enterprise, that's where we haven't had a chance yet to look at a lot of that equipment because we're just starting to get that equipment in. We've been able to start evaluating 802.11ac consumer equipment in August of last year. So 1 year ago this August, we were starting to look at consumer grade 802.11ac draft equipment. And so we had more time to look at that. The enterprise stuff we're just getting started looking at, so I can't speak to that quite as well yet. Which vendors do I recommend? I'll tell you on the consumer side, again, on the enterprise side, I'm going to stay away from that for this point. But on the consumer side, I've had good experiences with all of them that I've tried. But my personal best performance I've been able to achieve has been with the Asus 802.11ac wireless router. That's been the one I've been able to get to perform the best with actual throughput tests now. So this is dealing with the wired side of the device, getting it into the Wi-Fi side, out the wired side, and not just looking at the data rates that I'm achieving. So I've had really good luck with that one. Okay, so summary of facts then. We talked about 256 QAM and the impact this is going to have on our 802.11ac links, and the fact that we're not going to get 256 QAM 100 feet away or 2 or 3 walls away in most cases, sometimes not even a wall away from the access point. 160 megahertz channels may come in wave 2, but 80 megahertz is probably more practical even then for most of us. Again, I'll be glad to correct myself if we see enough value in 160 megahertz channels to go ahead and use them, and just have to very, very carefully plan those rollouts and implementations. Multi-user MIMO, this is something coming in wave 2 with support of standardized transmit beamforming, where we'll be able to effectively communicate with multiple client devices at the same time from that AP, giving us behavior more similar to a switch and less like a hub. Maybe we'll just call it a smart hub instead of calling it a switch. But at any rate, we'll be able to see a better overall throughput when we have these technologies to implement this capability as well. Okay, so this is what we've talked about in this presentation today, and the agenda that we've covered. What I'd like to do now is I'll just hold here for a few moments to give you a chance to chat in any other questions that you might have before we end this presentation today. So I'll just sit here and let you ask away at any questions you have. If you have no questions and you're ready to roll, that's the end of the covered material. And look for our webinar announcement for October. We have a special partner that's going to be doing a free webinar then. And look for our announcement of the webinar coming up in November. This will be available on YouTube as well. Okay, in a YouTube video about building a home lab, there's a mention of APs that allow capturing to a file. I'd be interested in a name, as I could not find some myself apart from Cisco devices. Can someone point me towards a few devices? I know APs that can capture your protocol to a file. It's not really just the AP, your frames, but AeroHive can do that as well, if I'm not mistaken. I seem to recall that they can do it. Anyone that's on here today right now hearing that, if you know of a vendor that you're using that does it, chat in and let us know if you know of an AP vendor that will also allow you to save to a file your protocol analysis. Thoughts on coexistence with ABG beyond what we have available in N? Well, obviously your coexistence with BG is just exactly what you had in N. That's still going to be the same thing because that's all you'll have in 2.4 gigahertz. Coexistence with A and N in the 5 gigahertz, they're just going to be protection mechanisms. So just like now, if you have a 40 megahertz channel, you've got a primary 20 megahertz, and then a secondary 20 megahertz, right? So the primary is used for your 11A clients. Even with an 80 megahertz, you're still going to have a 40 for 11N clients, and you're going to have a 20 for 11A clients. So that protection mechanism is still there, or that enablement is still there for backward compatibility. But obviously, when we start using that, just like in the past, it will definitely slow down our overall throughput on that network. No, the partner doing the presentation in October, I'm not sure their name. Julia in marketing will be sending that out a little bit later on, okay? What do I think about 802.11 AD? I think 802.11 AD will be, good in consumer, but I don't know how much we'll use it in enterprise. We'll have to wait and see. There might be some real uses for it. Here's an example. Wireless projection. I think it would be a great use for that in conference centers, so we don't have to interfere with our traditional wireless LANs in 5 gigahertz. So I think that would be a great use of 802.11 AD. We'll just have to kind of wait and see what might happen there and how many uses we might see in enterprise. Let's see. Any plans to update any event CWNP's exams to include 11AC? Yes, you will be seeing updates to particularly our CWNA exam in the next 12 months. So there will be updates so that it will be covering 802.11ac. Our courseware will be covering it. The official study guides will be covering it. So yeah, you'll see that. Motorola APs allow you to save it to a file too. Thank you very much. And Terasys AP does remote Wireshark. That's true. Good point. Blue Sockets allowing it as well. Can I provide a link to the CWNP blog where these slides will be available? Just go to cwnp.com and you'll see a link at the top that says blog. And again, you can watch for the update to the blog there, and I'll try my best to get it up before the end of business tomorrow, okay? It might be later today, but we'll get that up just as quickly as we can. Okay, and with that, thank you all very much, and good luck with your 802.11ac plans, and I hope to see you later in a webinar. So we're going to go ahead and close the webinar at this time. Thank you very much for attending.